Well, we're in section 2.6, looking at rational numbers. Before we do that, do you have homework questions? I did email a few of you that emailed me back because your answers seemed like you had it right and you just need a little nudge. But what is yours?
On section 2.4, and then it's the last one, 27.
Okay.
It's the first question.
Okay. So the first one right here?
Yeah, the first one and then the last one.
First one and the last one?
Yeah.
Okay. So we're looking at where would 1,957 be on a mod 7 clock? What they're doing is saying 1,957 is equivalent to what number mod 7. Okay, so we use the modular arithmetic like we did in class. We go ahead and take 1,950. Well, I'm not going to have room there, am I? Make a little more space here. Take 1,957 and divide by 7. So I'll get out my calculator. I get 279.57. So I want the whole number part. Okay, so 279, because that tells me how many times 7 goes into 1,957. And now I multiply the 279 times the 7. So if I take away 279 multiples of 7 from 1,957, I'm left with 4. So that's my remainder, and 4 is the number that they're looking for there. So they're saying do some mod 7 arithmetic. Now this bottom question wants to talk about m divided by n gives a remainder of r. So that's what we did. This was the m. It was divided by n, and it gives the remainder of r. Okay, let's look at this together. I'll just put the 4 o'clock on here, and then okay, so we need to look at modular arithmetic now, so let's go back to our number here. So this was the m, and it was equivalent to the r mod n. Okay. So let's go pick that choice. Do you have other questions you'd like to go over? Yes.
For that one, what did you put for the remainder? Because like it's the remainder for the top part you put as 4, like that was the remainder, but what you put 4 in the remainder as well?
It seems like it. Let's check. Yes.
Okay.
I think that's what their point is, that the remainder is doing the same thing as modular arithmetic, or what he called crazy clock arithmetic. Any other questions? Okay. Whoa, I didn't know I could do that. How do I get that off of there? Do I have to erase it all? I guess so. Okay. So study groups will be meeting 5:30 to 6:30 Monday nights, and there'll be a room announced later, right? Okay.
Do I have to then show you?
Yeah. Thanks. Yeah. Okay, so we'll get the room to be announced. But you're also able to meet with the tutors one-on-one. So if that time doesn't work for you, or if you'd rather schedule an online appointment with the tutors, you can do that at the tutoring center. Our first quiz is Wednesday. Anybody have any questions before we go on? Okay. So we're looking at rational numbers in section 2.6, and the author opens this section with the question, how can we prove that all numbers are rational? In other words, all numbers are fractions. We'll come back to that question. First, we're going to talk about, well, what is a rational number anyway? We look at a number of different types of numbers in this class. So today's focus is rational numbers. But to know what rational numbers are, we have a couple of other sets of numbers to talk about. So the rational numbers will be made up of integers. Integers are made up with the natural numbers. And we've talked about the natural numbers before. Does anybody remember what the natural numbers are? Yes.
Just like 1, 2, 3.
Perfect. 1, 2, 3, 4, and so on. Okay, so the numbers that our ancestors would have first found when they were doing counting, maybe counting their sheep or their new baby's fingers and toes. Okay, after that we get the integers. So the integers are, well, does anybody know what the integers are? Maybe somebody knows. So integers are all of these numbers plus their opposites. So I'm going to go dot, dot, dot in the negative direction, plus 0. So the integers are all the whole numbers. They don't have a little decimal or fractional bit to them. They're a whole number. But there are also negative whole numbers, positive whole numbers, and 0, not just the natural numbers. And that brings us to rational numbers. Does anybody see a word in rational numbers that will help us know what rational numbers are?
Ratio.
Yeah, good. Ratio. So ratios. Rational numbers can be written as fractions. Numbers that can be written as fractions, a divided by b, where a and b are integers, where a and b are integers, but b is not 0. Numbers that can be written as fractions a over b, where a and b are integers, but b is not 0, because we don't divide by 0. If you put division by 0 in your calculator, it gives you a big error. So 5 divided by 0, see, big error. Can't divide by 0. You can go the other way around. 0 divided by 5 just means you have a pizza cut into 5 pieces and you get 0 of that, which is sad. Okay, 0. All right. So I'm going to give you a list of numbers Maybe we should look at fractions first, though. Let's do that. So I had circles before in our little algebra review to talk about what these fractional values were. So let's just review that a little bit. If you have something cut up into 10 equal pieces, and you're picking out one of those, then it's one of the 10 equal pieces. So the number on the bottom tells how much the item is cut into, how many parts the item is cut into. So this is 1/10. Oh no, that's 1/8, isn't it? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Well, that's not fun. I wanted to compare 1/8 and 1/10, and I got a picture that has, I wanted to compare 100th and a 10th, and I got a picture that has eighths. This one has 100, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10 by 10. So that's 1 out of 100. So the denominator, the bottom of the fraction, shows how many pieces, the shape is cut into, and then we could color in a few more. Like we color in another one. Here we have 3 100ths. Okay, that tells how many of those we have. So I'm going to put a list of numbers down, and you go ahead and circle which ones are rational. So we have 1, 5, 0.7, 3/5, and 0. Go ahead and circle each of those numbers which is rational. Did you circle all of them? Which one would you not circle?
0.
Let's think about that. Can you write 0 as 0 over 1? So it's kind of a trick. So the whole numbers you can write as fractions. So the little trick here is that you can write them as fractions. So 0 divided by 1 is 0. So that's a one we can include. How about the 0.7? How do you write 0.7 as a fraction? Good, 7 over 10. So you will have a number of Wiley Plus homework problems that ask you to take decimal places and write them as fractions. So the trick is, well, what is the trick? How would I take 0.123 and write it as a fraction? Yes?
123 over 1,000.
Good, 123 over 1,000. And how did you know how many zeros to put down?
Because I used the decimal places.
Good, you looked at the decimal places. Okay, so if you haven't done this before, you look at the decimal places. 3 decimal places. So you want 3 zeros. So that's why we have the 0.7 is 7 over 10, because there was one decimal place, one number to the right of the decimal. So you'll have a number of problems like that in Wiley Plus. I think there's some with a number in front of the decimal too. So 243.1508, you would still only put 4 zeros in the number in the denominator. You'd put 243.1508 over a 1 with 4 zeros, because there's 4 decimal places to the right of the decimal point. So we're saying how many 10,000ths we have. Well, I did want to talk a little bit about what these decimal places mean. So let's take that 243 over 0.1508. So you have 243, plus you have 1/10 from the 1 in the tenths place, plus you have 5 1/100ths because of the 5, oops, thank you, because of the 5 in the next decimal place. You have no 1,000ths, and then plus you have 8 10,000ths. That's what that decimal means. It means that you have 243 whole things, and then this 1/10, so 1/10 would be 10 of these little boxes covered up. 10 100ths is the same as 1/10. And then you would have 5 of these little tiny boxes. And then you'd have 8 boxes which were really, really tiny. So we're going to be looking at some numbers and placing them in order. So let's make a couple numbers and tell me which is bigger. Okay, so we have the 243.15081 and 243.1507. Which is the smallest in these list of 3 numbers? Anybody? Yes.
The second one.
Second one?
2431507.
Oh, this one. Okay. Yep. This is smaller. That's good because you got to the 4th decimal place, and the numbers were all the same. All 3 numbers are the same up till the 0. But then when you come to the 4th decimal place, it's a 7. Okay. So this is the smallest. Okay. What's the largest out of these 3 numbers? First, middle, or last? Well, we said the last one's smallest. So, what's the largest? Which one? Do you know which one? Oh, anybody know which one? Yes.
The middle one.
The middle one. Good. Okay, so you are getting good at this. So because remember, this always means you're adding on a little bit more when you put another digit there to the right. So this number's a tiniest bit bigger than this one because you add on 1/100,000th to this other one. Oops, I wrote middle. Did I say middle? I was asking for largest, wasn't I? Yeah, sorry. This is the largest. So they're all the same if they weren't for this 4th decimal place and 5th decimal place. But then, when you go to the 4th decimal place, you look and see this number comes first. 7 comes before 8. So this one is smaller than the ones that have an 8 in the 4th decimal place. But then the next digit, the 5th decimal place, adds a little more on if that digit's not 0. So this is all the 243 plus the 1/10 plus the 5 100ths plus the 8 10,000ths plus one more little tiny bit, 100,000. Okay, so these numbers are very close. We have 243.1508 and we have 243.15081. And they're both rational, right? They're both rational. I'm going to ask you to find a number in between the two. So this is smallest. This is largest. Can you find a number in between the two? it might help to add more decimal places. So put a 0 here, and maybe put 2 zeros there, okay? So you can always add zeros without changing the value of that number. And that might help you as you go to find one that falls in between. Okay, let's work on this together. So we have 243.150. So it's the same up to here, right? And now I want to be bigger than this one on the left, so I have to have an 8 there to get a little bigger. But I have to be smaller than this one on the right that has a 1 right there. So I need to be smaller than that, so I'm going to put another decimal place that's a 0. So far I'm still the same as the one on the left. And I'm smaller than this one on the right. But now if I put my next decimal place down as whatever I want, then I'm in between. So the same up to here. But then you see how this has a 100 and this has a 1? This has a 8 followed by 100. This has an 8 followed by 0. So it's smaller than this one over here. And this one doesn't have that last 1, and so it's this one in between is bigger. So this is one, what is that, a millionth? Anyway, it's a tiny bit bigger than this one, because I have a 1 where there's a 0, 0, I have 0, 1. And it's smaller than this one on the right because there's a 0 there. So tell me some other numbers that you found that were in between. I know I can start like this. Somebody tell me how theirs ended. You have a 0, right? You should have a 0. And then what? 2. Perfect. Yeah, so that one is also in between. Okay. So we have to be smaller than this one over here. 1, 2, 3, 4, 5. In the 5th decimal place, we need to have a 0. But then I can put whatever I want and still be smaller than this number. And as long as I don't put a 0, I'll be bigger than this number. So look on your paper, see if you start out 0.15080, and then you can have whatever you want. Okay, you could put 3,279,000 if you wanted. Did I say 3 million? Then I should need some more zeros. How about 3,279? So that's how we tell relative size of numbers. Does anybody have any questions on fitting a number in between here? How many numbers fit in between? How many numbers fall between the number on the left and the number on the right? How many fall in between? Yeah, infinitely many. Good. Infinitely many numbers can squeeze in here because you can just keep, you could just start counting from here. 3,280, 3,281. Having those last digits just keep going incrementally higher. So there's infinite numbers between any two rational numbers. In fact, there's infinite rational numbers between any two rational numbers. These numbers that we wrote down, they were all rational, right? We could put them over the correct power of 10 and write them as a fraction. So let's just take the last one. 243,150,80,3279. And I'll put a 1 with how many zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So there's an infinite number of rational numbers between any two rational numbers. Because of the way our decimal system works, it's easy to see that in decimals. You can also do the same thing with fractions, but it's a little more work, so we'll avoid that. we're going to consider the Pythagorean theorem. We're actually considering the Pythagoreans today because the Pythagoreans had this question, and that's what we're looking at. How can we prove that all numbers are rational? In other words, all numbers are fractions. So the Pythagoreans were disciples or followers of Pythagoras. They were very fervent, and this is one of the questions they looked at. How can we prove that all numbers are rational? In other words, all numbers are fractions. So we're going to look at the Pythagorean theorem. Who remembers what that is? Somebody told me earlier in the week, right? With the triangles, the a squared plus b squared equals c squared. Or maybe that was last week we looked at that. So a squared plus b squared equals c squared in a right triangle. So we're going to look at the simplest right triangle. The simplest right triangle would have A and B, which are the legs, the parts that make up the right angle, be 1. So let's see what this missing side is. We'll call it C since that's the part in the Pythagorean theorem that it is, C. So we'd have the 1 squared plus 1 squared equals c squared. So 1 plus 1 is c squared, because 1 squared is 1 times 1. So 2 is c squared. So the square root of 2 equals c. So the Pythagoreans focused on the square root of 2 in their quest to show that all numbers are rational. So they're calculating the value of the square root of 2. And here's how that comes about. Let's go ahead and prove the square root of 2 is a rational number. Okay, so we want to prove the square root of 2 is rational. And this is the proof that you will need to be able to do for the quiz. So if you've been kind of drifting away, bring your attention back, okay? Prove the square root of 2 is a rational number. Well, first we assume the square root of 2 is rational, just like the Pythagoreans did. Well, what does it mean to be rational? We can just use our definition for that. So then the square root of 2 equals a divided by b. Okay, we're just defining what a rational number is. The square root of 2 equals a divided by b, where a and b are integers, and b is not 0. So if the square root of 2 is a rational number, we can write it as a fraction. Then we can do a little algebra with this. So that's why we have the algebra review. This is the most algebra we do through the whole semester. So let's take the square root of 2, which is equal to a divided by b, and we'll multiply both sides of the equation by b so that we don't have that fraction anymore. So on the left-hand side, you have the square root of 2 times b. Don't let your b slide under the square root symbol, okay? On the left side, you have the square root of 2 times b. On the right side, we have just a, because the b on the top of the fraction and the b on the bottom of the fraction cancel each other out. Okay, so we got rid of the fractions. That automatically makes a nicer equation. We can also square both sides. Remember, whatever we do to one side of the equation, we can do to the other. So So we square both sides of the equation. So you have the square root of 2b times the square root of 2b. So the square root of 2 times the square root of 2 is a 2, and the b times the b is a b squared. Now the Pythagoreans got to this point and were full of dismay. This is a problem. 2b squared equaling a squared. This is a big problem. It's off to the side here, I'll remind you. If I give you a number like 184 and ask you to find its prime factorization, you could divide out a 2 because it's even. 2 times 92. And you could divide out a 2 again. 2 times 46. And you could divide out another 2. 2 times 23. And 23 is prime. So you have your 184. It's 2 times 2 times 2 times 23. Now if I take 184 squared, I get 33,856. And if I ask you to factor 33,856, you should be able to do that without having to write all the work down. We already did all the work, right? What would the 33,856 have for a prime factorization? Somebody said it. 2 times 2 times 2, and then what? Pardon?
2.
Okay.
2. 2.
Uh-huh.
23.
Good. Good. It's 2 times 2 times 2 times 2 times 2 times 2 times 23 times 23, right? Because you already figured out the factorization, the prime factorization of 184. So you just have to write that down twice. So is anybody seeing why this 2b squared equals a squared was a big problem for the Pythagoreans? Why this shot a hole in their theorem here, in their theory? Every squared number has an even number of prime factors. Every squared number has an even number of prime factors. Because you double the factors in your number you're squaring. You just take your number that was being squared and you double the prime factors. So you always have an even number of prime factors. So I don't know what A is, but I know it has an even number of prime factors when you have A squared. And I don't know what B is, but I know B squared has an even number of prime factors. Well, the prime factorization of a number is unique. So I can't have, here I have an even number of factors in the prime factorization. Here I have in B squared an even number of prime factors in the prime factorization. But there's one more number, a 2. If you take an even number of factors and put one more on there, all of a sudden it's not an even number anymore. It's an odd number. So these two can't be equal. 2b squared is a number. It can't be equal to whatever a squared is, because this a squared has a even number of prime factors, and 2 times b squared makes an odd number of prime factors. So we're going to write that out, but not to use all those words that I said, because that's just too much to write, right? Let's see if I can find a shorthand version. Here it is. The number of prime factors appearing in a squared and b squared is even. The number of prime factors appearing in a squared and b squared is even. On the other hand, On the other hand, 2b squared has an odd number of prime factors. Two b squared has an odd number of prime factors because it has this even number of prime factors and one additional number. So a squared cannot equal 2b squared. A contradiction. What am I contradicting? Where's the error in this? Let's check. There's an error somewhere. Where's the error? So, did I do error in my algebra? B is not 0, so you can multiply both sides of the equation by b. You can square both sides of the equation. This is what a rational number looks like. So where is the error here? Anybody know where it is? This is the error. Okay, that's what we found out. It's impossible for the square root of 2 to equal a over b. It's impossible for the square root of 2 to be rational. So the square root of 2 is not rational. We call that irrational. The square root of 2 is irrational. It's not rational. So this proof that I gave you is proof by contradiction. You assume something's true and you follow the consequences through. That's a very nice way to prove things. It's often done in mathematics. Your author uses that as a life lesson to follow assumptions to their logical conclusion. Okay, ideas have consequences. Follow the ideas to the logical conclusion. You can learn a lot in life that way. Well, the Pythagoreans did really get disturbed by this. They took their math very seriously. The Pythagoreans reacted strongly to the disturbing discovery of irrational numbers or lengths, and they kept the idea secret. It is said that when one of their members was caught revealing the secret, he was taken on a boat ride and thrown overboard. Think we're joking? Proclus, around the 5th century CE, gave the brief account. It is well known that the man who first made public the theory of irrationals perished in a shipwreck in order that the inexpressible and unimaginable should ever remain veiled. And so the guilty man who fortuitously touched on and revealed this aspect of living things was taken to the place where he began, and there is forever beaten by the waves. Okay. So this is a proof you need to learn for the quiz, and hopefully nobody's ever going to throw you overboard if you don't know it, but this is for the quiz for sure. And again, this is one of the things that you need to practice, and so it will be worth more points, more like 9 or 10 points. You do need all of it. Okay, so sometimes students just give me this part. They're like, oh, this is algebra, I can do that. Okay, don't. You need more than that. You need all of it. Let's try another one, just to make sure, because these are kind of tricky, right? So proofs are always tricky, and we should practice. Excuse me. So we can do this idea with any square root that's not a perfect square. And which is not factorable. So let's prove the square root of 3 is irrational. Irrational. No, there. Prove the square root of 3 is irrational. So we'll take the same technique. Okay? We assume the square root of 3 is rational. Assume the square root of 3 is rational. Then, what does that mean? To be rational means that you can write it as a fraction. So then the square root of 3 equals a divided by b, where a and b are integers, and b is not 0. So we can do a little algebra after that. Okay, first we say what does it mean to be rational, and then we do a little algebra and follow the consequences. So we'll take the square root of 3 equaling a over b, and we multiply to get that denominator to multiply away. Multiply both sides of the equation by b. And we get the square root of 3 times b equals a. So that's a nicer equation, no fractions. And then you can square both sides of the equation next. So the square root of 3b times the square root of 3b on the left. The square root of 3 times the square root of 3 is a b, and the b times b is b squared. On the right you have a squared. And here's where the contradiction appears, because you have the a squared on one side with an even number of factors, and the 3b squared on the other side with an odd number of prime factors. Let's just write that out. The number of prime factors appearing in a squared and b squared is even. On the other hand, On the other hand, 3b squared has an odd number of prime factors. Three b squared has an odd number of prime factors. So a squared does not equal 3b squared. A contradiction. So square root of 3 is irrational or not rational. So we first say what the assumption is, that square root of 3 is rational. We say, well, what does that mean? It means we can write it as a fraction. We do a little algebra to bring us to this point of 3b squared equaling a squared. And then we realize this a squared has an even number of factors, like 6 or 8 or 10. But b squared would also have an even number of factors. And then there's this one more number that makes an odd number of factors. So these cannot be equal in their prime factorization. Does anybody have any questions on those at all? So we could keep doing this with like square root of 7 or square root of 11. Does anybody want to do this again? Feel like you got it? Okay. Well, let's continue investigating rational and irrational numbers then. So in 2.7, we look at all the numbers that you know that aren't that are on the number line, those are called the real numbers. So all the numbers you know that do not have an I in them are part of the real numbers. So I'll draw the number line. The arrow means this just keeps going on forever. And usually on the number line we write integers. You could write decimals or fractions, but usually we just write the integers because otherwise it gets real cluttered, right? So we looked at some rational numbers before, like 0.7. Or how about negative 5/3? And we can find the place for them on the number line. The number line is ordered. So we can find a place for all of these numbers on the number line. We just have to squeeze them in. Or maybe make the number line wider so you can see the area that you're interested in. So I have all integers written down so far, or rational numbers. Well, integers are rational numbers. So all rational numbers right now. Does anybody know? Oh, we just looked at some irrational numbers, right? Square root of 2 and square root of 3. So square root of 2 is about 1.4. So we squeeze it in here, a little bit closer to the 1 than the 2. Does anybody know any famous irrational numbers? Yes. Mm-hmm. Like pi. Yep, pi. And we looked at phi. Phi is an irrational number. What was phi? 1 plus the square root of 5 is about 1.6. We'll just put it about at 1.6. So phi, another irrational number. So you have the real numbers, and the real numbers are all the numbers on the number line. So they're all the ones that you work with, except the ones that have I in them. Has anybody ever done some with I? Okay, you don't have to worry about that in this section. Okay. So you have the real numbers, and then they split up. They split up into rational numbers or irrational numbers. Doesn't math have its own language? I mean, if you're talking about rational people or irrational people, you can kind of split the people up like that too, right? Okay, it means something different though. Okay. So we had our definition for rational numbers. It can be written as A over B, where B is not 0, and A and B are integers. Irrational numbers are real numbers that are not rational. Irrational numbers are real numbers that are not rational. Well, we're going to be looking at the decimal expansion of these numbers. So let's see if we can talk about their decimal expansion. So the decimal expansion okay, we're splitting them up. So the decimal expansion of rational numbers, it could just end, right? We looked at a number of rational numbers and we saw how they're able to be written as fractions from their terminating decimal expansion. So if the decimal expansion ends, then you can just easily write it as a fraction. I'm going to shut that door. So decimal expansion terminates. Okay, so come to a point where there's nothing but zeros left on the right. Or there's one other way to tell a rational number from its decimal expansion. Does anyone know what it is? Yes.
Is it when it repeats?
Yeah. Good. Or the end repeats. So, for example, 2/3, if you write that as a decimal, it has an end that just goes on forever, the 0.6s. So for irrational numbers, the decimal expansion does not terminate or end. So that's why we say pi is an irrational number. Its decimal expansion doesn't terminate. You can see signs with the first 1,000,000 digits of pi. In fact, there's one in our suite like that. And the decimal expansion doesn't end either. The definition that you'll see used on the quiz are these definitions right here. Okay. The real numbers definition is all the numbers on the number line. So those are the definitions that will be on the quiz. There, put that on there. So we'll pick up here and we'll talk more about the real numbers and how they split up into rational and irrational numbers on Friday. I'll see you then.